Synchronous motor power factor correction calculations. In this presentation, we're going to look at how we take a synchronous motor and do the power factor correction calculations in almost exactly the same way as what we did with three-phase power factor correction with capacitors. So it's going to be very similar. We just need to make sure that we watch out for a few of the minor pitfalls. Let's take a look at the basic process for a synchronous motor. If we had a 15 horse synchronous motor that was 100% efficient with 600 volt three phase, we know that there is DC excitation that energizes an electromagnet that is in the rotor. And if we operated at power factor of unity or power factor of 1, the watts and the VA would be identical. And how did I calculate the watts? Well, I took 15 and I multiplied it by 746. Now, in order for me to work out the current value for this particular motor, I line would be equal to, well, we take our VA and we would divide it by the line voltage times √3. So a synchronous motor operating at unity will have the lowest possible line current traveling to it or from it, however you want to consider it, as compared to either of the next two situations. So next one, what if we took that motor, exactly the same motor, and this time we adjusted the DC excitation and now we're running in lag? Well, if we run in lag, obviously we're going to draw some more current, and that's because we have a larger vertical. Remember, on unity, the power triangle was essentially a line. There was 0 VARs being generated. Over here, 19381.6 VAR. That means that we now have VARs that are required by the supply authority in order to run this motor. So it's going to draw more current. Notice the VA has gone up 22,380. And notice that the watts has remained exactly the same. This is still a 15 horsepower motor driving a 15 horsepower mechanical load. So we've gone from unity of 10.76 to this, a lagging value of 21.53 amps. Now this here is not really how you would want to run your synchronous motor. That wouldn't make much sense. Instead, we want to try to power factor correct. So if we were to adjust the DC excitation and swing it the other direction, what we would then notice is that, yeah, of course, the current's going to go up, and we can make it go up by an extreme amount. This is 0.3 lead, so this is really extreme. Notice the leading VARs. Notice the direction of the triangle. It has changed. It's now a leading VAR item. Is it still consuming watts? Yes, it is. 11,190. Has not changed in any of the three examples here. However, with a 0.3 power factor, we see 37,300 VA, which then, of course, leads to a much higher current. Again, because this is AC, consider once we go into leading, try to imagine that this item here is more supplying leading VARs back to the supply authority, as opposed to drawing that current in order to run. Well, with that out of the way, let's go through an initial example, sort of see how the system will work. So here's our first example, 600 volt three phase, and we have two motors. They're both 10 horsepower, they're both 100% efficient, and one of them is a synchronous motor. This one over here is just a standard skim motor, and it's operating at 0.6 power factor. So what we want to answer here is I line of the feeder when the sync motor is run at unity power factor. So the sync motor itself, its power factor is unity. How much current will be on the feeder, which would be these three conductors here. The second question we want to answer is, what would the line current be if the synchronous motor was run at 0.8 lag? Somewhat unlikely, but you never know. And finally, the third question here, let's use motor 2 or the sync motor to power factor correct motor 1. And we want to have the feeder at 0.98. And in addition to that, we have a few questions. So let's take a look at the information and how we're going to start the calculations. I always say sketch, sketch, sketch. I like sketches because sketches make things a little bit easier when they're illustrated. So I draw both the motors out, I give myself more space, and I start cranking out the numbers that I need. So we're going to start with the first question. The first question was simply, if this sync motor is run at unity, like this, then what's the feeder current for both of these motors? Well, we're first going to have to work out the watts. Notice the watts is identical for both motor 1 and motor 2. They're both 10 horsepower motors, and they're both 100% efficient. The skim motor, we're going to have to apply the power factor of 0.6 and apply it to my power triangle, and then use whatever method you are most comfortable with in order to work out the VARs and the VA. Typically, what I will do is I'll use the watts and the power factor to get the VA, and then I will use Pythagoras to get the VARs. On the other side, well, the power triangle is really just a horizontal line. The 7460 watts is equivalent to the VA, 7460, and there are 0 VARs. Okay, so next step, we want to take a look at how do we calculate the current? Well, in order to do that, we are going to have to add the values of the horizontal and the vertical components of the circuit together to make a total power triangle, which is what we have right here. So we added the power values, get 14,920. We add the Q values, but of course there is no Q for motor 2, it's a sync motor. So instead, this value down here is used for the vertical. At this point, we can start cranking out some numbers. So I'm going to use Pythagoras to get the total VA of this circuit, which would be right there. I'm then going to use my power and divide it by my apparent power, or my VA. So P divided by S gives me 0.832 lag. The total current in the feeder will then be the total S divided by E line times root 3. And what we end up with is 170.25 amps. Now, the second question that we had was, what will happen if we run this motor, the sync motor, at 0.8 lag? Okay, well, let's do another sketch then. And with this other sketch, we're going to try to capture all of that necessary information. So I'm starting again, but now what I have, 0.6 lag, this one's 0.8 lag. That's my synchronous motor. So let's go through the process yet again. Notice that this doesn't change, still 7460 watts. And when we look at the skim motor, that remains identical as well. That power triangle is identical to the previous example. If we look at the synchronous motor, of course, there's now going to be a vertical component, and that's because we're running in a deficit or a lagging power factor, which means also that the VA increases. If we then take a look at the total, we're going to use the same approach as we did on the previous example. We're going to build a large power triangle, and that power triangle is for the entire circuit. We're adding the two power values together, adding the two Q values together, and then we're going to use Pythagoras in order to work out the VA. This is the total VA of the whole circuit now. The power factor of the circuit is now 0.69. And the total feeder current has risen to 20.73 amps. Now, this situation here is not one that you would run into all the time. Perhaps they're just using the synchronous motor not to power factor correct, but instead to simply stay synchronized with another motor elsewhere in the process. Either way, seems like a bit of a waste when you could run it at unity. Which then brings us to our final question. And that was, if we took these two motors and this one, instead of running it in lag or unity, we ran it in a leading power factor, what would all the values of the circuit be? So another sketch coming up. And what we're doing with this one is exactly the same. We are working out, given the information here, they said, hey, we want you to run this so that the power factor of the feeder is now 0.98. So they've told us that. Now we've still got this motor 1, motor 2. We don't know the power factor of my synchronous motor, but this one sure hasn't changed. So what about the power triangles? Well, this one remains the same throughout the entire process. This one over here, the watts remains the same. And that's because the watts is the mechanical value, right? That is being output by the shaft of the motor. We don't know the S, the Q, or the power factor. All right, well, let's continue on. Total circuit. So we don't really know this value, but we know these. And we know power plus power equals total power. They've told us that the power factor is 0.98, so we should be able to use these two bits of information to work out the VA and the VARs currently in the feeder. So total VA, 15,224.48, and we can then use Pythagoras to get VARs, just over 3,000 VARs, and that would be the vertical component right here. Now, motor 1 VARs and total VARs, in the same way that we do power factor correction, we have to subtract the original VARs from the new VARs. So motor 1 VAR would be the original, total VAR would be the new corrected circuit VARs. And so what we end up with is 6917.08 VARs, which would be the capacitive VARs required by the synchronous motor. So this motor, we've got a whole bunch of different things that we want to know about. So let's take a look. The first thing we needed to calculate was the line current. Now that it's all power factor corrected, we want to calculate the line current. Well, the line current is going to require us to know, well, I would say primarily, we need to know this right here, the VA, the 15,224. That's total VA for the entire circuit, which means if we use E-line and root 3, we should be able to get the total circuit current. Let's take a look. So I-line feeder. First thing we're going to do is get our equation there. And the equation then is going to be 15,224 divided by 600 times root 3. And we end up with a value of current of 14.64 amps. The second item is for the sync motor. And the sync motor, we have a total S here of P squared plus Q squared. So the power squared plus the Q squared. And remember, we worked out the Q of the synchronous motor on the previous page. The Q of the synchronous motor was the capacitive VARs. The P we worked out at the very beginning of this calculation, which hadn't changed. It's still 7460. So the total S is 10,173.3 VA. The total current of my synchronous motor using my three-phase formula gives me 9.78 amps. And finally, the power factor of the synchronous motor is 0.73 lead. I utilize this information to assist as I'm going through the calculations to ensure that I've got the right numbers in the right places. All right, well, let's take a look at another example. And the second example is going to have us taking a motor and replacing it. So here's my second example. An install has 3 5-horsepower motors. Each motor is 80% efficient, 0.75 power factor, 600 volt, 3-phase. They're all skims. The questions we want to answer is right here. We want to know, whoops, there we go. We want to know what is the line current of each motor? What is the line current total for the entire feeder? And what is the total power factor? After we work out these values, we're going to take one motor and replace it with a synchronous motor. First things first, I-line of each motor. Well, the I-line of each motor can be calculated by using our horsepower times 746, giving us 3730 watts. And then divide by 0.8. This 0.8 is my efficiency. Remember, we're going from the shaft of the motor back to the electrical connections, which means the motor requires 4662.5 watts. Once I have that information, then I can go ahead and use my power factor to determine the VA. 4662.5 watts divided by my power factor gives me 6216.66 VA. Now the value of current is right here, 62,166.66 VA divided by E-line root 3 gave me 5.98 amps. And because these are all identical motors, we can easily determine the total feeder current by simply taking the value and multiplying it by 3. Now, don't get me wrong, you can't do this in every situation. It's only because the motors are identical in every way. Same voltage, same power factor, same efficiency, and same horsepower. Finally, the total power factor is equivalent to one motor because they're all identical. So the total power factor ends up being exactly the same as a single motor. Now to this installation, we're going to make a change, and we're going to exchange motor 3 with a synchronous motor. And what that's going to allow us to do is to power factor correct the 3 motors, or the feeder if you want to think of it that way. All right, well, let's take a look at how that's going to change things. Whoops, my mistake. The first thing we're going to do here is we need the information about how the system will work. So 2 5 horsepower, 80% efficient, 0.75 power factor motors. So those are the skim motors, and 1 5 horsepower synchronous motor. It's a little bit different. It's more efficient, and it's going to power factor correct the entire feeder to 0.98. All right, so very first step, what we're going to do is we're going to calculate some values for the skim motor. Now the skim motor, we already know the values for one of them because we worked that out in the previous example. Because the motors are identical, I can take this power triangle and multiply all the values by 2, and that would be the total skim values. If we shimmy over a little bit and get the sync motor, we see that really all we know right now is the watts because it is a 5 horsepower motor. And I took that by getting my 5 times 746 and dividing it then by 0.9 because it's 90% efficient. At this point, we add the vertical components together and the horizontal components together to get the total watts. And I am given the power factor of 0.98. They've told me it is a lagging 0.98 power factor for the whole feeder. Now the S total, as we've looked at before, can be calculated by taking the watts divided by power factor. And the Q, or VARs, of the circuit can be calculated by using Pythagoras once I have watts and VA. Well, let's take a look at the answers then for this final question. The things we wanted to know were first, I line of the feeder. I line of the feeder, how has that changed? Well, it's gone down. And we know this because we can calculate the total current by taking my total VA, as we did on the previous page, and dividing it by 600 times root 3, 11.39 amps. What are the leading VARs for this particular system? Well, as we see with most power factor correction, we're going to have to do an original. So what was the original existing VARs? And remember, there's only 2 skim motors here. Only 2, not 3. And then we need to subtract the new VARs from the system, which would be after power factor correction. And we end up with just under 7,000 leading VARs. Finally, for the actual synchronous motor, we start off with this information here. We know that it's 4144.44 watts, and we've just calculated the leading VAR value because we know this is capacitive. Now with these 2 bits of information, we can work out the VA, we can work out the power factor, the line current, and we're done. So let's take a look. S total, it's using Pythagoras, just over 8,000 VA. I line is my total S value, which is up here, divided by E line times root 3, 7.8 amps. And finally, power factor, we have a power divided by the S, and it tells me that this motor, or synchronous motor, is running at 0.51 leading power factor. So it is power factor correcting the 2 remaining motors that are in parallel with it on the feeder.